Today I'm going to talk about work and energy. So, what is work? Well, that may be difficult to explain because in physics, work is different from the normal definition of work that we use. So what is work in physics? Here's an example. The student lifts the book from the floor to the top shelf. Why does this work? It exerts a force, it moves, and its movement is in the same direction as the applied force. So what isn't work? And this might be different from what isn't work in normal situations, because again, the physics definition of work is different. Here's an example. Jonah holds the dog tightly by its leash to prevent it from moving. Why does this not work? There's a force, but no movement. And in the spreadsheet, there's actually more examples of what isn't work. So what isn't work? Other examples of what isn't work. Well, there's no force, or the movement is in the different directions. So it isn't in the direction of the applied force. Or like in this example, force but no movement. Okay, how to calculate work? There's two formulas for work. One of them that we usually talk about, W is FD, and the other is WFD cos theta. And that theta is an angle. And this cosine theta, we have to know why it's cosine theta. That's in trigonometry. So let's talk about that. Some component of force is in the direction of motion, and the fraction in that direction is the x component of the resultant vector. You can use vector analysis or trigonometry to find the x component. When the angle is 0, the cosine is 1. The whole force, 100% of the force, contributes to work done. Since cosine 0 is 1, and 1 is 100%, that's work in the direction of motion. Well, if it won't be a 1 or 0, it will be something between 0 or 1. Usually, there's going to be a fraction. For example, if you have that 45-degree angle, if you have a 45-degree angle between 0 and 90, then only half of that force goes in the direction of motion. Okay, what is energy? Well, this might be another confusing concept because we use energy all the time, and the definition of energy that we normally use is different from the physics definition of energy. Well, why do they have this light bulb over here? Because this light bulb actually has a few types of energy. Real energy is defined in physics. Well, what types of energy does this light bulb have? This light bulb has light energy that makes this light bulb shine. Well, how did it get the light energy? It can't be created or destroyed. So, it got transferred in some way. Well, the likely explanation is that this got transferred from electrical energy, and that electrical energy got transferred from some other type of energy. We don't know where that electricity came from. There's various ways from that electrical energy came from. Maybe it came from solar energy, or it came from water movement, for example. So energy is always going to be transferred. Oh, yeah, so here we have the water movement. But every single transfer of energy is not going to be 100% efficient. So any transfer of energy is going to release some amount of energy as heat because it cannot be destroyed either. And the heat energy cannot be easily used to make another type of energy. So it's kind of like the most useless type of energy that we have here, because heat energy can't easily be turned into something else. Some other type of energy that's useful. For example, electrical, light, and sound. Well, what was energy? It's the capacity to generate change. So how much capacity does this light bulb have to generate change or to generate something else? Like energy could be used to generate work, for example. And the individual types of energy can't be created or destroyed either, but they can be transferred from one type to another. So, if you have a conversion, let's say the thermal energy is a number, say 50, and electrical energy is a number, say 50, then you could maybe have this 90% efficient. So this electrical energy, there's going to be 40 of that remaining if it didn't get transferred anywhere. But instead, the thermal energy, there'll be more of it. There'll be 60. So there's a balance between. Well, why is this? So why? They still sum up to 100 because that transfer. All that transfer is not going to be 100% efficient, so it might not be so perfect. But this amount of energy in the universe is going to stay the same. It's not going to decrease from one to another. Okay. How to calculate energy? Why do I have this mountain? Well, because when you're at the top of this mountain, for example, this mountain, you will have a lot of potential energy. But there's lots of different types of potential energy. And if you are at the very bottom of this mountain, you will have lots of kinetic energy and no potential energy. And again, the same thing, the energy in the universe will remain the same, and the total energy of the system will also remain the same. Okay, so how to calculate it. And then here's a little bit of a principle. There's two types of energy, which can be classified as a type of kinetic energy, a type of potential energy, or a type of both. What is the formula for kinetic energy? Well, it might be different for some types of kinetic energy. So it's not always, but for some kinetic energy, it would be 0.5 mv squared, half mv squared. And the formula that for potential energy, but only gravitational potential energy. Well, why is it only gravitational potential energy? Because of its gravity. Because of gravity, so it's associated with gravity. PE is mgh. Okay. Thank you. Bye.